14,411 feet, 26 glaciers, 80,000 people inside the official Lahar hazard zones. The United States Geological Survey calls it one of the most dangerous volcanoes in the country, not because of lava, because of what the mountain becomes when it moves. Mount Rainier sits 54 miles southeast of Seattle. On a clear morning, it is visible from the waterfront, from the upper floors of office buildings, from the highways feeding the metropolitan area. It looks permanent. It looks solid. It is the most glaciated peak in the lower 48 states, carrying roughly 1 cubic mile of ice across its flanks, 5 to 6 times more ice than every other volcano in the Cascade Range combined. The United States Geological Survey designates Rainier a decade volcano. That category is reserved for volcanoes whose combination of eruptive history and proximity to populated areas places them in a separate tier of concern. Rainier shares the list with Vesuvius and Merapi. The reason for the designation is not the lava. Lava moves slowly enough to walk away from. The reason is what the mountain carries above its valleys and what happens when it releases it. 5,600 years ago, the summit of Mount Rainier collapsed. The event began with a phreatomagmatic eruption, an explosive encounter between rising magma and groundwater trapped inside the upper edifice. The blast was not what destroyed the mountain. It triggered a slide. The slide removed approximately 2,000 feet of mountain top. The volume of debris was 3.8 cubic kilometers, enough material to bury the entire city of Seattle under roughly 20 feet of rock and mud. Within 2 kilometers of the summit, that debris had already transformed. The clay inside it held the water. The water made it flow. What started as a rock slide became a lahar, moving wet concrete down every river valley it could reach. It traveled at 43 miles per hour. It filled the White River Valley to depths of 300 feet. It buried forests. It did not stop. 70 miles from the summit, the flow reached the sea. It did not stop there either. The wave of material continued moving underwater, beneath what is now the port of Tacoma, beneath the Seattle suburb of Kent, for an additional 12 miles below sea level before it finally came to rest. This event has a name: the Osceola Mudflow. It covered approximately 210 square miles of the Puget Sound lowlands. Near the modern city of Auburn, the deposit sits 260 feet thick, 2/3 of it below current sea level. 8 wood samples pulled from inside the flow all return the same radiocarbon date. The carbon results are consistent. The geology is not in dispute. Today, 6 cities stand on its hardened surface: Tacoma, Auburn, Kent, Enumclaw, Sumner, Puyallup. Every one of them built on the body of a single afternoon's event. None of them existed when it happened. All of them rest on it now. This is not a lava story. Lava is slow, visible, and loud. What Rainier produced 5,600 years ago gave no meaningful warning to anything in its path. There was no wall of fire. There was a wall of moving rock and clay and ice water, 100 feet high at its leading edge, faster than a highway speed limit, filling valleys from wall to wall. The questions that follow from this are not small ones. How does a mountain reach the sea? Why is the primary threat from a major Cascade volcano something that has nothing to do with fire? Why do 80,000 people live inside mapped inundation zones? And why do some of those zones carry a modeled warning window of 5 minutes between detection and destruction? Who decided which valleys would carry zoning restrictions and which would not? And could it happen again with no warning at all, no eruption, no tremor, nothing that lets anyone get out? A lahar is not lava. The word comes from Indonesian. It describes what happens when volcanic rock, clay, and water are forced together under gravity and set into motion down a slope. The result is not a flood. It is not a landslide. It is closer to flowing concrete, dense, fast, and carrying everything it touches. A flood moves around obstacles. A lahar moves through them. Where a river parts at the base of a bridge pier, a lahar wraps the pier, strips it, and takes the bridge. Where a flood recedes and leaves mud behind, a lahar hardens in place. Bridges trapped inside a deposit are crushed flat. Vehicles are folded. Buildings disappear into material that sets like poor-quality cement and does not give them back. The physics of a lahar at full discharge are not intuitive. A large event can move 2.5 million cubic meters of material past a fixed point in a single second. That figure does not translate easily into human scale. The average flow of the Mississippi River, compressed into one pulse and weighted with rock and clay, approaches it. Boulders the size of vehicles move inside the flow as if they weigh nothing. The leading edge can stand 100 feet high. If hot pyroclastic material was incorporated at the source, the internal temperature can reach the boiling point of water. The distinction from lava matters because the behavior is different in every way that affects survival. Lava is slow. Most lava flows can be walked away from. A lahar cannot. Lava is hot enough to be visible at a distance, at night, from miles away. A lahar arrives at river speed or faster, brown and opaque, indistinguishable from floodwater until the leading edge reaches a structure and the structure ceases to exist. Mount Rainier is positioned to produce a lahar the way a reservoir is positioned to produce a flood. The fuel is already assembled. The water is in the glaciers. The mountain carries 26 named glaciers, roughly 36 square miles of ice, with a total volume estimated at approximately 1 cubic mile. That is 5 to 6 times more ice than every other Cascade volcano combined. The Carbon Glacier alone is 700 feet thick at its center. It is the largest glacier by volume in the contiguous United States. A 60-story building could stand inside it from base to surface and still have ice above. The rock beneath it is volcanic. The heat below that rock is active. The slope connecting all three runs directly into inhabited river valleys. The fuel does not need to be ignited. It needs only to be released. Gravity does the rest. Ice becomes water. Water meets clay. Clay becomes the medium that carries everything downhill at 40 miles per hour toward the sea. This is not a mountain. This is a water storage facility built on top of a heat source. Speaking of geological systems hiding catastrophic potential, there is a narrow inlet in Alaska where a single earthquake dropped an entire mountainside into the sea, generating a tsunami taller than the Empire State Building. We'll get to that. Subscribe and turn on notifications, or just find out about it when a 1,700-foot wave drops from the sky. Now back to Mount Rainier, because the interior of this mountain has been chemically attacked from within for hundreds of thousands of years. The agent is sulfuric acid. The source is the volcano itself. Hot gases rich in sulfur rise through the cone from the magma chamber below. They meet groundwater trapped inside the upper edifice. The reaction produces sulfuric acid, and the acid dissolves the volcanic rock surrounding it. What remains is not granite, not andesite, not basalt. It is clay, specifically a soft water-absorbing mineral called smectite, which loses structural cohesion the moment it becomes saturated. This process has a name: hydrothermal alteration. In plain terms, the mountain has been rotting from the inside, quietly, continuously, for longer than the human species has existed in its current form. Geophysical surveys have measured the result. Helicopter-mounted instruments scan the upper mountain and detect altered rock by its reduced magnetism and lower electrical resistance. The surveys concentrate on a section of the upper western flank called Sunset Amphitheater. What they found there was not a pocket of weakened material. It was a clay-rich zone exceeding 500 meters in thickness. That is more than 1,600 feet of softened, water-saturated material suspended near the summit of a 14,000-foot peak. Below it, river valleys drain directly into the western suburbs of Tacoma. Two geologists, David John and Thomas Sisson, spent years climbing the mountain and drilling its slopes. They were trying to map the rot with precision, to determine how far the alteration had spread and how deep it ran. The samples came back from the laboratory, and the picture they produced was not ambiguous. Their conclusion, filed with the United States Geological Survey, fit inside a single line. The upper west flank, in its current state, is a continuing collapse hazard. Not theoretical, not conditional on an eruption. Continuing. The word matters. Continuing means the process that built this hazard is still running. The acid is still being produced. The rock is still being converted. Every year that passes, the altered zone grows slightly larger, and the material inside it holds together slightly less well than it did before. From a distance, none of this is visible. On a clear morning in Seattle, the mountain rises above the horizon in a clean white mass. The summit looks carved from a single block. The flanks appear solid. Snow and ice cover most of the upper elevation. The impression is of something permanent and stable, a geological fixture that has stood for millions of years and will continue standing. That impression is wrong. The surveys, the drill cores, the laboratory results, all of them point to the same internal condition. The mountain that appears white and solid from the city is, in the region of greatest concern, structurally closer to a saturated sponge than to competent rock. The Sunset Amphitheater Zone is not a seam of weakness running through otherwise sound material. It is a mass, more than 1,600 feet of it, sitting above valleys that hold suburbs, roads, and people, held in place by slope angle and the residual cohesion of material that the volcano has been chemically dismantling for centuries without pause. Beneath the snow and the lava cap, the upper west flank is closer in structure to wet clay than to stone. 5,600 years ago, Mount Rainier's summit collapsed. The trigger was phreatomagmatic. Magma contacted groundwater deep inside the cone. The resulting explosion was not what destroyed the mountain. It was what started the slide. The blast destabilized a summit already weakened by hundreds of thousands of years of acid and clay. What followed was a sector collapse. Approximately 2,000 feet of mountaintop peeled away from the eastern flank in a single motion. The volume of debris was 3.8 cubic kilometers of rock, clay, ice, and water. That figure is difficult to hold in the mind. It is roughly the volume of 3 Hoover dams filled to capacity, moving at once, downhill. The transformation happened fast. Within 2 kilometers of the summit, the debris was no longer behaving as a rock slide. The clay inside the material held water. The water made the mass fluid. By the time it reached the upper river valleys, it was a lahar, moving like concrete poured from an enormous height, filling every channel it entered from wall to wall. The speed at the leading edge reached 43 miles per hour. Entire forests disappeared beneath it. The valley floor rose by 300 feet in places as the material stacked up against its own leading edge and kept pushing forward. Trees that had stood for centuries were not knocked down. They were buried. The deposit was not layered over the landscape. It replaced the landscape. The flow did not stop at the base of the mountain. It did not stop at the foothills. It did not stop at the lowlands or at the edge of the Puget Sound. It traveled 70 miles from the summit to the sea. And then it kept going. The mass was so large and moving so fast that it continued beneath the surface of the water, traveling an additional 12 miles below sea level before it finally came to rest on the floor of the sound. The mud is still there, beneath what is now the port of Tacoma. Beneath the Seattle suburb of Kent, the deposit sits under modern infrastructure, under developed land, under city streets. It does not announce itself. In some locations near the modern town of Auburn, the hardened material lies 260 feet thick, 2/3 of it below current sea level. The total area covered by the Osceola Mudflow was approximately 210 square miles of the Puget Sound lowlands. The date comes from wood. 8 samples recovered from inside the deposit were submitted for radiocarbon analysis. All 8 returned the same result, the same 5,600-year window. The carbon-14 results are consistent across every sample. The geology is not in dispute. Today, 6 cities occupy the hardened surface of what the Osceola Mudflow left behind: Tacoma, Auburn, Kent, Enumclaw, Sumner, Puyallup. None of them existed when the flow passed through. All of them were built on top of what it deposited. The streets are flat because the flow leveled the valley. The soil is productive because volcanic material breaks down into fertile ground. The location felt convenient. The river was calm. The land was wide and open. It was open because the Lahar had cleared it. The nations who lived in this region before any of those cities existed carried a different understanding of the mountain. They had watched it from the valleys. They had named it from what they knew. The Puyallup indigenous peoples called the mountain Tahoma. Different languages, different generations, the same warning. 500 years ago, the western flank of Mount Rainier collapsed again. The event has a name, the electron mudflow. The date, established by modern dendrochronology, is 1507. The deposit traveled 60 kilometers down the Puyallup River Valley. At the point where the flow entered the lowland, near the community now called Electron, the mud was 30 meters deep. Nearly 100 feet of moving concrete filling a river valley in a single afternoon. At Orting, 20 miles downstream, the material settled at 26 feet thick. Everything in its path was gone. Douglas fir trees 3 meters in diameter were torn from the soil, carried for miles, and buried where they fell. They are still there. Radiocarbon dating has confirmed it. The bark on several of them was preserved well enough to count the final growth rings. The first geologist to formally describe the electron mudflow was Dwight Crandell of the United States Geological Survey. In 1963, he published a detailed account of the deposit. He could not pin down the trigger. The radiocarbon date he obtained came back as 530 years before present, plus or minus 200 years. Useful as a rough boundary, not useful as a calendar. 30 years later, a geologist named Patrick Pringle was driving through Orting when a construction site exposed buried trees in the cut bank. He collected core samples from roughly half a dozen long-dead Douglas firs. One of them, designated LE001, had a clean ring sequence. Its outermost ring corresponded to the year the tree died. Pringle and his colleagues compared those rings against regional master chronologies, the same method used to date the dead cedars on the Washington coast. The result was unambiguous. The electron mudflow killed those trees in the late summer of 1507. That was the year. The next question should have been simple. What triggered it? It was not simple. Geologists searched the deposit for a tephra layer, the thin band of volcanic ash that settles onto the ground before a major eruptive event and gets buried underneath the flow material that follows. It was not there. They looked for any correlated record of summit activity, any regional indicator of magmatic disturbance in or around 1507. Nothing matched. No ashfall in lake sediment cores from the surrounding region. No documented eruption in the oral record. No sign of volcanic precursor activity of any kind. For decades, the working assumption was that the evidence had been lost. Perhaps the eruption was small and its deposits had eroded. Perhaps the volcanic material lay beneath the Lahar itself, hidden from sampling. The assumption held because the alternative was uncomfortable. The alternative is this. The largest documented Lahar at Mount Rainier in the last 2,500 years may have been triggered with no eruption at all. This is now the working hypothesis of the United States Geological Survey. The electron mudflow began as an avalanche of hydrothermally altered rock high on the western flank, near Sunset Amphitheater, the same zone where surveys have since measured more than 1,600 feet of clay-rich mush suspended above the river valleys below. Its onset cannot be correlated with any volcanic event. 3 possible triggers remain on the table: a small phreatic explosion that produced no preserved tephra, a hydrothermal pressure release, steam and acid-saturated fluids forcing their way through weakened rock until the slope gave way, or a tectonic earthquake with no connection to the volcano's magma system at all. That third possibility carries a specific weight. Mount Rainier sits in the western foothills of an active subduction zone. Beneath the Pacific Northwest, the Juan de Fuca plate is sliding under the North American plate at roughly 4 centimeters per year. The interface locks. It stores stress for centuries. Then it releases, in events of magnitude 8 or 9, events that shake the ground across the entire region for several minutes at a time. The last such release occurred in 1700. The interval since then has already exceeded the historical average. A great Cascadia earthquake shaking hydrothermally altered rock for several minutes does not need to be centered near the volcano. It needs to be strong enough. The clay-rich material on the upper west flank does not require a volcanic trigger. It requires a mechanical one. Cohesion lost. Slope angle exceeded. Gravity finishes the rest. The electron mudflow, in the words of William Scott of the United States Geological Survey, sort of keeps us honest. A modern town sits on top of that deposit. The city of Orting, Washington. Population approximately 4,400. The streets are flat because they rest on 20 feet of hardened lahar. The soil is fertile because it is volcanic. The valley is wide, the river is calm, and the location is convenient. None of that is coincidence. All of it is consequence. Richard Iverson is a debris flow specialist at the Cascades Volcano Observatory. He and his team built a computer simulation of what happens when the west flank of Mount Rainier lets go. They fed in the geometry of the slope, the volume of ice, the clay composition of the upper edifice, the shape of every river valley downstream, the position of every town. Then they ran the model. What came back was a set of arrival times. Inside Mount Rainier National Park, the Lahar reaches inhabited zones in approximately 5 minutes. Outside the park boundary, the window expands, 15 to 60 minutes depending on the valley and the distance from the source. Orting sits roughly 30 miles downstream from the Puyallup Glacier. The model gives it less than 30 minutes from the moment a flow sensor trips to the moment the leading edge arrives. That figure assumes the Lahar moves at a sustained pace and encounters no significant obstruction in the upper valley. Neither assumption is conservative. 80,000 people live within the official Lahar hazard zones, identified by the United States Geological Survey. Pierce County's broader estimate, accounting for the full inundation footprint of an Osceola-scale event, places approximately 2.5 million people in the affected region. The same estimate puts roughly $40 billion in property at risk. Bridges, hospitals, rail lines, the port infrastructure that handles cargo for the entire Pacific Northwest corridor. Pierce County has installed 42 outdoor warning sirens across the Puyallup and Nisqually valleys. Acoustic flow monitors sit mounted along the upper river channels. The instruments detect ground vibration from a moving lahar and trigger automated alerts to county emergency managers. Sirens follow within minutes. The system is tested on the first Monday of every month. Residents drill walking routes to higher ground. The required pace is fast. The route is roughly 2 miles. The system works. The system can only warn after the lahar has already started. The acoustic monitors sit in the upper valleys, not on the summit. A flow has to be moving, carrying enough mass to register on the instruments before any alert goes out. By the time the sensor trips, the lahar has already formed. The clock in the valley starts running from that moment, not from the moment the slope fails. In some valleys, there is no gap between those two events worth measuring. The warning infrastructure is real. The sirens are maintained. The drills are practiced. The evacuation routes are marked and cleared. What the infrastructure cannot manufacture is time that does not exist in the geometry of the valley. Inside the park, the arrival window is not a planning horizon. It is not enough time to notify, confirm, broadcast, and move. It is barely enough time to understand what the instruments are saying. 5 minutes is not an evacuation window. It is barely a recognition window. There is one fact about Mount Rainier that the textbooks introduce slowly, almost reluctantly. Pierce County has identified its lahar inundation zones. It has restricted construction inside them. The hazard maps are published. The sirens are installed. The evacuation routes are marked. That work is real and it is documented. But Pierce County is not the only county in the path of an Osceola-scale event. The Osceola Mudflow did not stop at a county line. It ran 70 miles to the sea. It buried what is now Kent. The deposit sits beneath that city today. Measured, dated, confirmed by 8 wood samples from inside the flow. King County contains Kent. King County is more populous than Pierce. King County lies directly in the documented path of the largest lahar this mountain has ever produced. King County has no zoning restriction for volcanic hazard. None. The standard explanation places the primary risk in the Puyallup and Nisqually valleys, which drain through Pierce County. That framing is accurate as far as it goes. It does not go far enough. A full Osceola-scale collapse does not stop where the smaller flows stopped. The geology of the 1507 electron mudflow and the 5,600-year-old Osceola deposit are not the same event, but they share the same source and the same physics. 2 counties sit on the same documented flow path. One restricted development in the inundation zone. The other did not. The mountain is unaware of the boundary between them. The recurrence interval for major lahars at Mount Rainier is 500 to 1,000 years. That figure comes from the deposit record layered in the river valleys across the last 10,000 years. It is a probability, not a schedule. But the arithmetic is uncomfortable. The Osceola mudflow occurred approximately 5,600 years ago. The Round Pass mudflow followed roughly 2,600 years ago. The National Lahar moved down the Nisqually Valley somewhere between 2,200 and 500 years before present. The electron mudflow occurred in 1507. The interval since the last Great Lahar is now 519 years. The mountain is inside the lower bound of its own recurrence window, not approaching it, inside it. Scientists monitoring Mount Rainier have observed accelerating changes in recent decades. The exposure of altered rock material has progressed faster than models predicted from the historical record. This raises questions about whether traditional recurrence intervals remain valid under current warming conditions. The mountain's behavior is increasingly shaped by both ancient and contemporary processes. These combined pressures create a scenario without modern precedent. There is a second variable the previous cycles did not carry. Mount Rainier has lost approximately 39% of its glacier area in the last 120 years. As the glaciers retreat, more of the hydrothermally altered rock on the upper west flank is exposed directly to the atmosphere. The soft clay-rich material that hydrothermal acid has been building for hundreds of thousands of years is no longer covered. Freeze-thaw cycles work on it. Rain saturates it. Snow loading shifts across it. Each cycle pulls at the cohesion of material that was already losing cohesion on its own. The weakening is not hypothetical. It is measurable. It is ongoing. In 2025, glaciologist Maury Pelto reported that the mountain now appears visibly darker from the cities of Seattle and Tacoma. Gray rock is exposed where white ice and snow once covered the mid-mountain slopes. That visual change is not cosmetic. Exposed rock absorbs solar radiation at a rate that ice does not. Absorbed radiation accelerates further melt. Further melt exposes more altered rock. More exposed rock absorbs more radiation. The feedback loop runs in one direction only, and that direction is toward instability. The same process that has been working on this mountain for hundreds of thousands of years underground is now accelerating at the surface, on the same western flank, above the same river valleys, above the same towns. The ice was not just a feature of the mountain. It was a load pressing down on fractured and altered material, moderating temperature, slowing the freeze-thaw fracturing that works on rock from the outside, while the acid works from within. A mountain shedding its ice is also shedding its restraint. Every civilization assumes the landscape it inherits is the landscape it has. The valley where Orting sits looks like a valley. It is not. In the geological record, it is a delivery channel, shaped by the last great flow and waiting for the next. The plain where Tacoma's port operates is not a plain. It is the leveled surface of an ancient debris deposit, hardened over centuries into something that resembles solid ground. The fields outside Auburn and Kent are not fields. They are the flat top of a buried catastrophe, fertile because the material that killed everything in its path eventually became soil. 3.5 million people see the mountain on clear days. It is visible from the waterfront, from the highway, from the upper floors of buildings in Seattle and Tacoma. Most of them know it is a volcano. Many of them do not know what kind. The ice volume has been measured. The clay zones have been mapped. The collapse mechanism has been modeled. The arrival times calculated. The sirens installed, the evacuation routes marked, the drills practiced, the hazard zones published. The components of the system are understood. What remains uncertain is only the timing. A great Cascadia earthquake shaking weakened rock for several minutes. A small phreatic explosion that leaves no preserved record. A gradual mechanical failure on a slope that has been getting softer for hundreds of thousands of years. Any of these could be the trigger. None are predictable in the operational sense. The geologists have done their work. The emergency managers have done their work. The mountain holds the next move. The question is not whether the mountain will move again. The question is whether the morning it chooses lines up with the moment anyone is paying attention.